Hey, everything we've been doing in the first three lessons have actually been related to rational functions. A rational function is basically it's a fraction with a polynomial in the numerator and a polynomial in the denominator. And the parent function is 1 over x, which the graph for 1 over x is shown right here. And we already did some graphs of this inverse function in the first lesson we did. And so we actually have asymptotes here. And if you remember our discussion with exponential functions and logarithmic functions, we talked about asymptotes there. And when we're dealing with the parent function, 1 over x, the asymptotes are the x and y axis. So as the graph continues to the left and to the right, it's going to get closer and closer to the x-axis. And as it moves towards the middle, it gets closer and closer to the y-axis. But it never crosses them. The one thing you'll notice on this graph is that when they've noted the asymptotes, the x and y axis, they've used dotted lines for that. One of the things you're going to be doing is you're going to be graphing rational functions today and tomorrow. And while you're graphing the rational functions, you have to make sure that when you express asymptotes, you express them with dotted lines on your graph. Your graph itself will be represented with solid lines. The asymptotes will be represented with dotted lines. They're dotted lines because they're really not there. You're just using them as a boundary for your graph so that your graph does not cross them. So in this case, our vertical asymptote is x equals 0, and our horizontal asymptote is y equals 0. And we can take that parent function 1 over x and we can transform it by moving it left and right, moving it up and down, stretching it out vertically, okay, which are things that you did in lesson 1. You actually were stretching it out vertically, doing reflections and like that. So here is one form of what a rational function looks like. And if you look at that handout I gave you, you should have a little half sheet of paper there. You look at that handout, you'll notice on the first line of that handout is this rational function here. And this tells you specifically what those things are for. The A talks about a vertical stretch or compression. And if it's negative, then it's a reflection across the x-axis. The interesting thing is I had this exact same conversation with my Algebra B students today because we were talking about vertex form of a quadratic function which involves a, h, and k also. And all three of them do the exact same thing. Whether you're talking about a quadratic function like in chapter 5 of the Algebra 2 book, or whether you're talking about the inverse function, okay, a rational function. Right? That h represents a horizontal shift. If h is positive, it moves it to the right. If it's negative, it moves it to the left. K is a vertical translation or a vertical shift. If it's positive, it moves the graph up. If it's negative, it moves the graph down. Okay? Now, here's the basic thing that happens. Okay? If I have an h and a k, right, basically, if you want to draw the new graph, you take the vertical asymptote and you move it h units, and the horizontal asymptote you move it k units, and then you just adjust your graph. Okay? That's basically all that's happening, is that the center of this graph here, 1 over x, is at the origin, and when I put h and k in there, numbers other than 0, then all it does is move this point here at the origin to that new spot. So my vertical asymptote and my horizontal asymptotes are still going to be there. The only thing might be different is if we have a value for a that's other than 1. But you figured out how to do that because in lesson 1, we had numbers like y equals 20 over x, or y equals negative 8 over x. Okay? All possibilities where you could make translations or transformations just by stretching it or shrinking it. So we're going to use the graph of 1 over x as our guide, describe the transformation here, and graph each function. So what I need to do is I need to recognize either the value of h and the values of a, h, and k. So in letter A here, you have g of x equals 1 over x plus 2. What's the value of a? Okay, a is 1. What's the value of h? It's not 2. Okay, the value of h is, this says x minus h. So the value of h is negative 2. If you remember conversations from Algebra B, whenever we have transformations and it's a horizontal thing, it's always the opposite. Okay? So h, it always involves a horizontal shift in everything you've done with transformations. And so h always involves the opposite number. So if it says plus 2, it means negative 2. All right? What's the value of k then? Okay, 0. There's no number out here, so k is 0. So what we're going to do then is we're going to take this graph of 1 over x, and we're going to move it according to that. So here's what the graph of 1 over x looks like this. And so the asymptotes that were here, and the asymptotes are dotted lines. So the asymptotes are the x-axis, or the y-axis, and the x-axis. There's where my asymptotes are right now. Because this has a value of h is negative 2, what's going to happen to that graph then? What's the transformation that takes place? A is 1, so that doesn't affect it at all. When you multiply by 1, you get the same number, right? Okay. K is 0. All right, is that going to affect anything? All right, because k was adding. I'm adding 0. Okay. H is a horizontal translation. It says if it moves left, if h is negative, less than 0, moves to the right when h is positive or greater than 0. So since h is negative 0, or negative 2, this means that we are going to shift it 2 units to the left. That means then that this asymptote here is now going to move over here to negative 2. So when I draw my graph, basically all I'm going to do is I'm going to take this graph just as it is, and I'm going to move it over. Come on, be my friend. Okay. All right, so I move it over. Oh, there it moved. Okay. So instead of there being a point at 1, 1, this point here is now at negative 1, 1. I moved it over 2 spaces to the left. So I have the same exact graph. All I did is slide it over to the left. Letter B. G of x equals 1 over x minus 3. What's the value of a in this problem? 1. Okay. The value of h is 3, okay, because it's in that same form. It says x minus h, so h is positive 3. And what about k? 0. Okay, we're not adding anything. So a is 1, h is 3, k equals 0. So once again, we're going to take this graph, not that, which has asymptotes on the x and y axis. And since h is 3, then we have a horizontal shift 3 units to the right. So our vertical asymptote here moves 3 units to the right, which means then that my graph so this now, come on, there you go. So I put in minus 3, the graph moves 3 units to the right. And don't forget one very important thing that they don't put on their graphs is these graphs go on forever. So make sure you draw arrows. One thing you'll notice though is that they do not cross the asymptotes. Okay? The asymptotes are dotted lines and the graph does not cross them. Okay? So this one was a shift 2 to the left, and this one was a shift of 3 to the right. So all I need to do when it's written in that form, okay, and we'll be using a different form later on, but when it's written in that form, we need to identify A, H, and K, and then move the graph accordingly. Okay, I don't want you to graph these, okay? I just want you to tell what the transformation is for them. So identify A, H, and K, and tell what the transformation is. Okay, so let's get a little more specific then. And this graph, so for all those rational functions, the graph is what's called a hyperbola. In other words, this graph has reflection symmetry. Okay? So if you look at these graphs back here, they actually have reflection symmetry. So if I drew the line y equals negative x in here, okay? All right, so if I drew the line that goes right through here, then these are reflections over that line. Or reflections over the origin, which is one of the things that you may have learned in geometry. Well, now we're going to be specific and identify the vertical and horizontal asymptotes and domain and range. Now, when we identify the asymptotes, vertical asymptotes, and this is what's on your, one of the things that's on your paper, vertical asymptotes are lines x equals h. So if you're going to identify h, the vertical asymptote is x equals that number. Okay? It's a line, so you have to say x equals. You just can't give me a number. It has to say x equals. Horizontal asymptote is the line y equals k. Okay? Now notice the domain and range. The domain, x cannot equal h because I can't divide by 0 because the value of h would make the denominator 0. And the range is y is not equal to k. So if you can identify h, vertical asymptote, x equals that number, domain, x cannot be that number. Because it causes it to be 0. Because you notice that at that spot, okay, at h here, the graph doesn't exist. At the vertical asymptote, the graph doesn't exist because it gets closer and closer to that line, but doesn't actually touch it. For our range, okay, our horizontal asymptote, the graph gets closer and closer to that line, but it never touches it. So there's never, so this graph right here, 1 over x minus 3, you're never going to have an x value of 3 because that would make the denominator equal to 0. And you'll never have a y value of 0 because that would cause it to be undefined also. So here they want us to identify the asymptotes, domain, and range of this function. So once again, we need to identify a, h, and k. That's the first thing we want to do. Because if we can identify a, h, and k, then we just say vertical asymptote, x equals whatever h is. Horizontal asymptote, y equals whatever k is. Domain, x cannot be h. Range, y cannot equal k. And that's the one thing that I forgot to put on here, okay, is about domain and range. So you might want to, in the vertical asymptote and the horizontal asymptote, and those rows, you might want to add that domain is x is not equal to h, and the range is y is not equal to k. Right? So you know domain and range. Those are things you're going to have to find. So you might want to add them to that row. It's right here. Okay. Vertical asymptote, x equals h. So the domain, x is not equal to h. Horizontal asymptote, y equals k. So the range, y cannot equal k. And you don't need to put that vertical line there where it says x such that. That's what that means. That's back in beginning of the Algebra 2 book where they're doing set builder notation. You don't need to know. Okay. So what's the value of a here? Okay, a is 1. How about h? -3. And k is, okay, -2. So this is really easy. All right. And I'm going to use abbreviations. VA is vertical asymptote. Okay. VA is a vertical asymptote. It's really easy. X equals -3. And then, so when I draw the graph, I'll have a dotted line, a vertical dotted line through x equals -3. Because what would happen if I put -3 here? What do we get? We get 0. Okay, can I divide by 0? No. Okay. My horizontal asymptote, HA, y equals -2. So that means I have a horizontal line to y equals -2. Domain then, x cannot equal h, and h is -3. X will never be -3. the range y cannot equal k, so negative 2. So y will never be negative 2. And if I wanted to draw this graph here, it's just the same graph we've been drawing. What's that? Here and here. If a is negative, it'll be there and there. Okay? When a is positive, it's in the first and third quadrants, okay? Upper right, lower left. And if it's negative, it's in the second and fourth, so upper left, bottom right. Right? You guys all know the quadrants, right? 1, 2, 3, 4. Okay, so they don't want you to graph this, but identify the asymptotes, domain, and range. So if you know h and k, now these rational functions that we're working with are called discontinuous functions because there's a gap in them. Okay? They don't continue on forever from left to right. Okay? Polynomials that we've worked with before, exponential functions, logarithmic functions, well, not logarithms, but exponential functions, and all your polynomials, those are continuous functions because they go on forever from start at infinity in the left and go to infinity in the right. Okay, and do a whole bunch of stuff. But these are discontinuous functions because they either have a gap or a break in them. And most of these have a gap in them. Sometimes they have a hole in the graph. All right, we're going to talk about holes tomorrow. So here is a graph of the exponential function, or excuse me, not the rational function, x minus 3 times x plus 2 in the numerator and x plus 1 in the denominator. Now, this is where we're looking at the bottom part. So you've got that big bold line there that separates your sheet there. And we're going to look at rational functions still, but a different form of them. And so we're going to talk about zeros and vertical and horizontal asymptotes. Well, today we're going to just focus on zeros and vertical asymptotes. The horizontal asymptotes, when it's written in the different form, is actually a little bit more difficult to see for most people, but when you see the little trick there is involved, it shouldn't be that difficult. Okay, now, this says if p of x over q of x, so that means we have a polynomial in the numerator and a polynomial in the denominator. In other words, like x squared plus 3x plus 5, or x minus 3, or x cubed plus something. Those are polynomials. So if I have a polynomial in the numerator and a polynomial in the denominator, in other words, there's a single fraction bar, there's no plus k, there's just everything is in the numerator and the denominator. Zeros for this function are when the numerator equals 0. Vertical asymptotes are when the denominator equals 0. Okay? So the x-intercepts or the zeros for this function are when the numerator equals 0. Vertical asymptotes are when the denominator equals 0, which that was true with the other part we were doing. Okay, but it's still true here. So when they ask us to find the zeros and the vertical asymptotes, the first thing we have to do is factor anything that needs to be factored. Okay, or anything that can be factored, we want to factor it. So can I factor the numerator here? Yes or no? Okay, I can. All right, and Alyssa, what do I get when I factor it? Okay, x plus 4 and x minus 1 over x plus 3. Okay. So the zeros are when the numerator equals 0. All right? So where does the numerator equal 0 here? -4 and +1. So my zeros are at -4 and +1. Okay, I'm not going to say x equals, I'm just saying the zeros are these numbers. Okay. Vertical asymptotes are when the denominator equals 0. And this is still a line x equals. So when does this denominator equal 0? At what value? Okay, at -3. So my vertical asymptote, x equals -3. Now, this graph does not have a horizontal asymptote. All right, now I'm going to explain that to you tomorrow. Okay, gets a little technical, but it's not. There's not one there. So I'm going to plot my points. Okay, I have a 0 at -4 and at +1, and I have a vertical asymptote at x equals -3. So that's a dotted line right here. So when I start graphing it, those are the first things I'm going to do. Mark the zeros and the vertical asymptotes. Now, before we go on and finish the graph, I want you to notice something of the other graphs that we've done so far. All right, so notice this connection. When the graph is moving from left to right, I'm going to be moving from left to right here. Okay? As it moves from left to right, this graph is going down to -infinity, right? Okay. Notice what happens when I cross over the asymptote. It's coming then from +infinity. Okay. Left to right. Okay, go down, goes to -infinity. When I cross over the asymptote, it's coming from +infinity. Okay. Every graph you make, it will always, if it goes to -infinity, all these rational functions, if it goes to -infinity on one side of the asymptote, it's going to come from +infinity on the other side, or vice versa. Okay, it never is on the same, never goes the same direction. Okay, -infinity comes from positive. Right. This one here, same thing. So this graph here then. Can anybody tell me where the y-intercept is? Okay, we found x-intercepts where it crosses the x-axis. Anybody know where the y-intercept is? What's the value of x for the y-intercept? If it intercepts the y-axis, the value of x there is what? 0. Okay? So if you put 0 in for all the x's, what do you get? Because remember, if I multiply by 0, I get 0. If I square 0, I get 0. So in the numerator here, I would get what? -4. In the denominator, I would get, okay, +3. So that's -4 thirds, right? So the y-intercept is, oops, right in here at -4 thirds. All right, so this actually tells me something. This tells me, because this graph then is going to have to be going like this, right? Because it's got to connect these 2 points. Right? There's no other zeros, right? So it can't come back down here, right? And it can't cross the vertical asymptote. So take out your calculator, right? And I want you to graph this on your calculator, right? So you can see it. And make sure if you got an 83, those nice black ones, you put the numerator in parentheses and the denominator in parentheses. You do it from the original. Make sure you put the numerator in parentheses and the denominator in parentheses. Okay, if you're not going to write it as a fraction, then the numerator must be in parentheses and the denominator must be in parentheses. Otherwise, your graph will be incorrect. Oh. The numerator's got to be in parentheses. That's it. Oh, it has happened for you too, unless you put it as a fraction. All right, I want to see what you got on your calculator. Okay. You got to put the numerator in parentheses and the denominator in parentheses. Okay. All right, Nick, compare yours with Rachel. All right, compare your two calculators together. Chris, you got it? All right, I want you to, you got it. Compare your two calculators. And look at, you guys look at Nick's calculator also. Okay, now, all of you have graphs that look like this, right? Except some of you have a graph to where you actually see a line here, correct? Okay. The calculators have a slight error to them, and it's a technology problem, that what it does is that these lines should not be connected, correct? Okay. But the 83, unfortunately, it connects them. And so you could kind of think of that as the asymptote drawing it in there. It doesn't draw it, but you can think of it that. But here's the thing. If you make this -3 the center of your calculator, okay, of your screen, then it won't be there. All right, so here's what I want you to do. Go to your window. Okay, this is specifically for the people with the 83, but if you have a line drawn there, it counts for you, okay? And I want you to go from -8, okay, which is 5 left of -3, right? What would be 5 to the right of -3? Okay, +2, okay? So make your x window, your min, x min -8, your x max +2, and then redraw it. And that line will no longer be there.